This is section ICT 21, group number 2 in physics class. Today, we're about to present you something regarding light. So, if you are thinking about reflection and refraction, you are right. Sit back down there, relax, and think with us for a 20-minute discussion. Light is always an interesting subject, especially when talking about how it is applied. We can always see its properties in action very prominently in fiction, and they get quite exciting when portrayed in the TV screen. As much as we enjoy the light show, not many can say that they enjoy or realize the subject matter of light in real life, no? Well, that is understandable. Light itself seems very simple and practical, but it is indeed very complex to grasp. For example, at this point in time, most probably already know the statement that the stars we see in the night are already dead. We are aware of the fact, but not about how it happens. How does it happen anyway? You see, stars are twinkly, shiny, and big, but they are super far away from us. We know that the speed of light is fast, but the distance is so massive that their light needs some time to reach us, here on Earth. Unfortunately, some stars do not survive before their light actually reaches our eyes. This gives us a hint that everything that we see is only light. However, that is another topic for some day. For now, let's jump to the common ground, reflection.
Reflection of light. Have you ever wondered why images are formed in a mirror? This is due to the bouncing back of the part of the light incident on the mirror. This bouncing of light from a smooth surface is called reflection. The amount of light a surface reflects depends upon the nature of the surface, angle at which the light beam strikes the surface, and the nature of the material on which it is incident. Reflection is of two kinds, namely, regular reflection and irregular reflection. Regular reflection takes place when a beam of light falls on a smooth and polished surface like a mirror. In regular reflection, the reflected light goes only in a fixed direction. Irregular reflection takes place when a beam of light falls on rough surfaces like walls, wood, etc. Here, the different portions of the surface reflect the incident light in different directions. Hence, the reflection becomes diffused. Irregular reflection is also known as scattering of light. It is due to scattering of light we are able to see the objects around us.
The process of light returning back from the mirror is known as reflection. The surface that reflects the light is known as the reflective surface. It is often useful to consider a single ray of light coming in and striking a surface, and we can represent that ray with a straight line. It comes in and strikes the surface at a certain angle. The angle that strikes is called the angle of incidence. Now, it's crucial to remember that we always measure these angles relative to the normal. So, take the point at which the light ray strikes, and draw a line perpendicular to the surface at that point. Always remember that the word normal means perpendicular. So this one is the surface normal at that point. The angle here that the ray of light makes with the normal is what we call the angle of incidence. So, the incoming ray is the incident ray, and the angle that it makes with the surface normal is called the incident angle. And the ray which hits the surface bounces off, and this angle here is called the angle of reflection. This ray bouncing off is called the reflected ray. Now, the law of reflection is very easy. It simply says that the angle of incidence equals the angle of reflection. So, you can say this angle is equal to this.
There are two types of reflection: specular and diffuse. Specular reflection occurs on smooth surfaces. Diffuse reflection occurs on rough surfaces. The rougher the surface, the more diffuse the reflection. We can perceive the direction of and distance to the things we see because reflected light behaves predictably. We trust our eyes because light always reflects in accordance with the laws of reflection. This means that the path of reflected light can be determined given knowledge of the path of the incident ray and the orientation of the surface. On a very smooth surface, lines normal to neighboring points along that surface are parallel to each other. Since the angle of reflection depends upon the orientation of the normal, a set of parallel incident rays encountering a smooth surface will reflect so that the angles of reflection are all the same. During specular reflection, the reflected rays will be parallel if the incident rays are. The organization of the incident rays is retained by the reflected rays, and this preservation of organization allows us to see images in mirrors. In contrast to specular reflection, diffuse reflection occurs on rough surfaces. In diffuse reflection, all of the reflected rays still behave in accordance with the law of reflection, but the roughness of the surface results in variation in the normals along the surface. With this variation, normals at neighboring points are no longer parallel to each other. Since the angle of incidence depends on the normal line at the exact point a ray hits, the incident angles for a set of parallel rays will not be the same, and each reflected ray will have a different angle of reflection. In other words, the rays scatter. The orientation of the normal lines at neighboring points along a surface differentiates specular from diffuse reflection. If the normal lines are parallel, reflection will be specular. If they are not parallel, reflection will be diffuse. Note, this is roughness at the microscopic level. Diffuse reflection occurs on surfaces that are smooth to the touch, such as paper, and specular reflection occurs on curved surfaces, such as a funhouse mirror. Specular reflection is useful. Without it, we would not have cameras or mirrors. However, it is diffuse reflection that is central to our ability to see the world. Aside from the limited number of luminous objects, such as light bulbs and the sun, everything we see around us is visible because of diffuse reflection.
The earliest accounts in the study of light's reflection stems back to around 300 BC. People back then appeared to have already a viable understanding on how light is being reflected. This traces back to Euclid, a legendary Greek mathematician who conducted many experiments, but also discovered that light travels in straight lines, and the angle of reflection and incidence are equal. The great discoveries came many years later in the 10th century AD by the Arab scientist Al-Hazen. He wrote over 100 books, and his most influential writings was from the field of optics. Al-Hazen gave experimental proof about the nature of light, the basic principle of reflection via mirrors, and the structure of the eye. His theory about the eye contradicted those of Euclid's, that the eye does not send out rays. Instead, the light is reflected via the object in which our eye beholds. So basically, as a recapitulation, reflection of light is the event where a light bounces off back after hitting an object. This is what makes us see all the objects, as it allows light to travel more and directs vision to our eye. The light that will hit the object is called as the angle of incidence. The light that bounces off the object is called as the angle of reflection. In specular reflection, light is reflected from a smooth surface. Therefore, angles of the incidence and reflection will be equal. In a diffuse reflection, the rough surface will cause light to bounce into every different angle. Therefore, what we see is also dependent upon the nature of an object's surface and its material. By now you should have realized that everything you see is only just light. Therefore, What we see is also dependent upon the nature of an object's surface and its material. Leaves are green. That means that leaves absorb all the other colors, except green light, and so we can see that leaves are colored green. When no light is reflected, it will be black, undoubtedly, causing us to see nothing. So whenever every wavelength of light colors is absorbed, the object will appear to be white, just like your t-shirt. Be thankful that for the sun, the creation of light bulbs, and most importantly, your eyes, that they exist. Without them, we cannot reflect even upon ourselves. Refraction is another important property of light, and should not be confused with reflection. Though they work hand in hand, refraction totally changes the way how we see images. This makes it a great tool for optical illusions and create tricks that really shakes up our minds. It can either be a problem or a benefit.
Refraction. Here you can see a pencil dipped in a glass beaker and a coin placed at the bottom of a trough. What do you observe? The pencil looks bent and the coin appears raised. Why does this happen? This is because when light travels from one optical medium to another optical medium with different optical densities, there is a change in the direction of propagation. This change of direction suffered by a ray of light as it passes obliquely from one optical medium to another optical medium with different optical densities is known as refraction.
A light ray diagram shows the behavior of light based on the light ray model. The light ray that hits the surface is called the incident ray. The angle at which it hits is called the angle of incidence. This angle is defined as the angle the light ray makes with a line normal or perpendicular to the surface. The path a light ray travels after encountering the surface can be predicted based on the incident angle and information about the surface. Light rays that reflect follow the law of reflection. The law of reflection states that the angle of reflection is equal to the angle of incidence. Light rays that pass through the interface are transmitted rays. These rays bend. This bending is called refraction. The amount a light ray refracts is described by the angle of refraction. This is the angle between the transmitted ray and the normal. The angle of refraction is also called the angle of transmission. The direction and magnitude of the refraction depends on the relative densities of the two media and the angle of incidence. Light traveling from a less dense to a more dense medium refracts towards the normal, making the angle of transmission less than the angle of incidence. This behavior is exhibited by light moving from air into water. Light traveling from a higher density to a lower density medium refracts away from the normal, making the angle of transmission greater than the angle of incidence. The greater the difference in density between the two media, the greater the refraction. The greater the angle of incidence, the greater the refraction. For light traveling from a more dense to a less dense medium, there is an angle beyond which the light will not pass through the interface. This angle is called the critical angle. A light ray with an angle of incidence equal to or greater than the critical angle will always reflect, taking a path consistent with the law of reflection.
People from ancient times always wondered why sticks appear to be broken when dipped into the water. This is where the term refraction began, as it was meant to be broken back. The actual law of refraction was discovered in the early 1600s by a Dutch mathematician and geodesist, Willebrord Snell van Rooyen. He formulated the discovery he made, named today as Snell's law, which is basically what we have discussed earlier. The application of this law is being put into our great benefit for our time. Big examples are the telescopes we use to gaze at the stars. They focus the light and make distant objects appear brighter, clearer and magnified, using mechanisms to apply the refraction equation. Our eyes bend light, and that is why we see things clearly. However, there are people that may have sight problems, so they go to optometrists and ophthalmologists. They may say that we have a refractive error, and might suggest you wear contact lenses or eyeglasses to fix this problem. But today, we have advanced technology that this can be permanently fixed by refractive surgery. Unlike reflection, which is pretty straightforward mathematically, refraction has some ins and outs you have to lay on the paper to be accurate in computations. The Snell's law helps us go through these computations, such as finding the index of refraction and the angle of refraction.
Now here's Snell's law. He said this: Ni times the sine of I, that's the sine of that angle, equals Nr times the sine of angle R. And that fact is all you need to calculate a refraction. Just remember what the different pieces of that equation are. I is the incident angle, so you have the sine of the incident angle, and R is the refracted angle, so you have the sine of the refracted angle. And these n's are the indices of refraction for the two different materials. Ni is the index of refraction of the material where the incident ray is, and Nr is the index of refraction for the material where the refracted ray is. Here's how we calculate the index of refraction for a given material. The value N is always equal to this ratio. The speed of light in a vacuum which is 3 times 10 to the 8th meters per second, divided by the speed of light in the material. So, light goes very fast in a vacuum. It goes a little bit slower in other materials, so we have a bigger number in the numerator. So our value for N is typically larger than 1. But that's what N is. It's the speed of light in a vacuum divided by the speed of light in a material. And that equation is commonly written like this. N is equal to C, that's the speed of light in a vacuum, divided by V, where V is the speed of light in that particular material. And here's a simple example showing the use of that equation. Suppose we're told to find the speed of light in water. Well, the equation is N equals C over V. C is the speed of light in a vacuum. V is the speed of light in water. That's what we're looking for. And N is the index of refraction for water. So we just need to solve this for V. And the algebra is real simple. Just take this guy and that guy and trade places. So V is equal to C over N. And C is the speed of light in a vacuum. That's 3 times 10 to the 8th meters per second, divided by N, which is the index of refraction for water. And we looked that up. It's 1.33. So when we do that, we divide and we get 225,563,909 meters per second. And we would probably just round that to 226 million meters per second. Now here's an example just showing the use of Snell's law. If a light ray traveled from air into glass with an incident angle of 58 degrees, what would be the angle of refraction? Well, it's a good idea to draw a diagram, so we'll just draw a rectangle for the piece of glass. And let's draw an incident light ray coming in with an incident angle of 58 degrees. And you don't have to measure this exactly to do the calculation, but let's just draw it to get a visual picture. So this is I right here, this angle. And we know that I is equal to 58 degrees. And I'll go ahead and draw the refracted ray. This refracted angle down here, R, I don't know. But I do know this. I know that NI times the sine of I is going to equal NR times the sine of R. And NI and NR are the indices of refraction. Now what are those? Well, NI is the index of refraction for air because the incident ray is in air. That's 1.00. NR is the index of refraction for the glass because the refracted ray is in the glass, and the index of refraction for glass is 1.52. So those are the numbers that I'll use, and I'm trying to find R. Now I can't find R directly, but algebraically I can solve for sine R. So I just divide both sides by NR, and I get this. Sine of angle R equals NI times the sine I over NR. I've just taken this equation and rearranged it algebraically to get that. Now I can put in all the numbers on the right hand side and I get a value for sine of R. So NI, what is NI? The index of refraction where the incident ray is. That's 1.00. Now sine of I, what is that? Well, I is 58 degrees, so this is 1.00 times the sine of 58 degrees over NR. And what is NR? That's the index of refraction where the refracted ray is, 1.52. And make sure your calculator is set in degrees. Type in the sine of 58. You don't have to do times 1 because that will still be the same number. Divide by 1.52 and you get 0.5579. Now that's not your answer. What you just found was the sine of R, and sine of R is 0.5579. We have to find R. If the sine of R is 0.5579, then R will be the inverse sine of 0.55. Oh, and that should be a 79 right there, 0.5579. So R is the inverse sine of 0.5579. And you punch that into the calculator and it comes out to 33.9 degrees. And that's the angle of refraction that we were trying to find.
Light has many properties, and that includes reflection and refraction. Reflection is when light bounces off a surface. Refraction is when light is being bent through a surface. But before that, we must understand that we are able to see, because light is able to move through our space. The materials, the objects, anything in this world is only a stepping stone for our vision. Without light, there would be no color, as colors are only light of different wavelengths. Without light, we will be in a state of darkness. We hope this video is successful in enlightening you about how important light is, and how fortunate we are to live in a very wonderful and delightful world as healthy, seeing and believing human beings.